Hello, welcome to my giant 3D printer individual project for MEng Robotics Year 3 Stage 4 by myself, Benjamin Job. In this video, including a presentation, I will be going through the sections Introduction and Background, which includes an overview and the background itself, and a full description of the project, existing solutions, features, aims, achievements, and its purpose and use cases, design and build, including a schematic of it, challenges and planning in the build process and design, and conclusion and demonstration at the end. This is the project overview. The 3D printer is designed to be portable and adaptable for transporting as 5 modules and being rigid. It can also have additional modules which can be swapped out on the endpoint location for multiple print heads or for other work such as for CNC milling or laser cutting. This is the background and description of the project. Because of the wheeled design and gap in both sides of the project for extrusions for a railed use, this allows a large to up to unlimited theoretical build volume. Most stationary and small in scale printers have fixed build volumes. In comparison, this 3D printer with its wheeled drive means it can print in different locations with large build volumes due to its Y movement being wheeled or railed. Here are some of the existing solutions. Some 3D printers have infinite Z belt, which means it can build infinitely in the Z direction. This usually uses a core XY configuration, and there will be a conveyor belt integrated into the printer. I also found a small prototype printer which uses a SCARA configuration with a robotic arm, which can be able to print in the same way with a larger scale, but because of its design and size, it could be unstable. Other type of printers exist, such as Cartesian, Delta, and Polar, and in theory these could have large, but not necessarily infinite Z or Y build volumes, and not giant volumes in the way that my printer would be able to. This is a review of the aims and deliverables for my project. For it to be portable and adaptable for modular capability in the future, a large extendable dimension in the Y for up to theoretical and limited, but definitely large build volumes. Self-leveling, which is automatic or mostly automatic, and being able to print at an angle with different slicers and use different modules, as in the first deliverable. This is a review of the achievements that I made in this project. I made a portable adaptable design, which ended up being 5 separate modules, which can be assembled together very easily with wing nuts. A large extendable wide dimension printing using wheeled or railed operation. A self-leveling, which is either manual or probe operated and is a mesh leveling. And the ability to print at an angle for continuous printing at different orientations. This is the purpose and its use cases. The sectors for this kind of printer can be in construction, modeling, or art industries, for example. It can be used for prototypes, or it can be used in the workplace. And it can be used and has the ability to print onto fixed surfaces, which opens up applications such as Braille for floor markings, or things such as bollards onto the floors directly, or a separate external build volume or plate. These are the design concepts, including the hardware iterations throughout the build process. This is the full original design. I sketched this idea, and it has a smaller side profile and a smaller base because of it. The design was improved through in-between designs where the profiles were becoming thicker and more modular. This ended up turning into a more simplified and evolved design which used C-beams and wooden side panels. Its normal current testing configuration is 1 meter approximate width and depth, and a larger just over 1.5 meter x-axis, which can be swapped to up just over 1.5 meter, as has been done, or different widths depending on use case. This is a few pictures of the build. And here is a summary of the final design, showing the drivers used and the motors. NEMA 23 and NEMA 17 motors were used, with NEMA 23 used for the y-axis more recently and the z-axis. Hardwood ply supports were used as structural elements, and C-beams were used for structural integrity, specifically for the actuators. Also, bespoke and open source 3D printed components were used throughout the build process for mounts, clips for cable management, and any connecting components. Here's the schematics of the build. As you can see, there's a computer which can connect to the printer via Wi-Fi or USB connection through a USB hub, a switching transformer providing power 12 volts to the shield and the Arduino controller through step down. There's also external drivers and drivers that can run through the shield directly, and end-stop switches which are used as minimum end-stop travel limits, and the print head assembly connected. This is a review of the main project challenges. Firstly, I needed to make sure that the 3D printer would be rigid and so would be stable when it's printing. To do this, I used a hardwood frame and I used aluminium extrusions. Most of them were C-beam, and this also included cross struts and supports to improve the rigidity. Secondly, I had some problems with the y-axis drive, so I used higher torque NEMA 23 stepper motors in combination with a pulley system which was geared to provide even higher torque. I also used rubber wheels for non-slip operation and bearings to make this operation smooth. Lastly, I thought about transportation by starting off with a modular design. This was further implemented by using wing nuts and other electrical connections for the easy disassembly of the modules. Logistics and planning. I used a virtual environment and a VR headset to help visualize the project in VR. This was used to organize thoughts, visualize the scale, and put any questions or answers which may be related to the model. I also pointed to parts of the model which I needed to work on and develop. and this allowed me to create an overview of the project as I was going along. These slides show a review of the initial and updated Gantt charts, showing the plan, research, idea formulation, design, and the push forward build process in the updated Gantt chart. In conclusion, I successfully designed and built a mobile 3D printer which is capable of printing large-scale prints onto fixed or removable surfaces, which uses a wheel design or can use wheel design with rails. This railed or wheeled configuration can give much better printing performance, but the rail configuration, although has been built in design, hasn't been tested, which will be good to prove its better printing performance in this operation. It could also be developed further by adding additional end modules, such as traditional hot ends extra, or for laser cutting or mill functionality, such as a router or a laser end for laser cutting. Now I will demonstrate how I designed the 3D printer and how its movement and designs were chosen in a 3D model, including it shown in real life and an overview of its features there. As you can see, I created a full 3D model of the entire project to test its strength and for simulation purposes, as well as rendering how it would look like in real life. This also allowed me to check tolerances and made sure that the build could be fitted together and easily removed for transportation. As you can see as I zoom in, on the right hand side at the back there's a Raspberry Pi and a 12-volt power supply which can power the whole printer. Also, with the Raspberry Pi, it has ability to run over Wi-Fi to control the printer through the Arduino board, which is shown at the top here with the LCD screen. Also shown is the external stepper motor drivers used for the Y-axis. At the front of the project, you can see a filament reel used for the extrusion of the filament. And at the side, right here, you can see the belt system and pulleys used for the Y-axis. Around the whole of the project, you can see end stops, which are coloured slightly red. And at the back of the project, you might be able to see the small brackets and clips used for the cabling and cable management. Here is a video showing an overview of the entire build in real life. A USB hub allows the Raspberry Pi to be powered on individually, and bed leveling is available from the LCD screen for probe or manual bed leveling. This is the homing and movement system of the 3D printer. I will select the Auto Home option on the LCD screen, which will home the X, then Y, then Z in that order. As you can see, it accurately homes itself to the floor.